Hello everyone, we are presenting our functional programming mini-project titled Student Marks Analyzer, developed using Haskell. This project demonstrates how functional programming concepts such as pure functions, immutability, recursion, higher-order functions, and modular design can be applied to a real-world scenario in education data analysis. In educational institutions, analyzing student marks is a common requirement. Teachers often need summaries such as average marks, top performers, and grade distributions. Our goal was to build a reliable, predictable, and maintainable system to analyze student marks using functional programming principles, ensuring correctness and ease of testing. Our project is structured in a modular way, following functional programming best practices. Main.hs, this is the entry point of the program and handles the menu and program flow. Datatypes.hs contains all algebraic data types such as student, grade, and summary. Processing.hs includes all pure functions that perform calculations and data transformations. IOHandler.hs handles all input and output operations, such as reading files and printing reports. Utils.hs contains reusable helper functions. This separation allows us to clearly isolate pure logic from side effects, which is a key functional programming principle. This function is a pure function because it always produces the same output for the same input. It does not modify any state, and it does not perform any side effects such as printing to the screen or reading user input. Because of this, the function is predictable, reliable, and very easy to test. In functional programming, data is immutable, which means once a value is created, it cannot be changed. In this function, the student record is never modified. Instead, we compute new values such as the average, maximum, and minimum marks and return them as a new summary record. This approach avoids unexpected changes, makes the program safer, and simplifies reasoning about the code. In this project, we use algebraic data types to model real-world entities such as students, grades, and summaries. For example, the student type represents a student with an ID, name, and a list of marks, while the grade type clearly defines all possible grade values. Using ADTs allows the compiler to catch many errors at compile time, improves code readability, and ensures that our program handles only valid data, which increases overall correctness. In this part of the code, we use higher-order functions such as map and sort by. These functions take other functions as arguments, which allows us to transform and sort collections of data in a very concise way. Instead of using loops, we declaratively describe what we want to do to the data, which makes the code cleaner, more readable, and easier to maintain. This function uses Foldl, which is a functional abstraction over recursion. Instead of using traditional loops, Foldl repeatedly processes each element in the list and accumulates the result. This allows us to safely and efficiently compute the grade distribution in a declarative way. Using folds makes the code more expressive and avoids common errors found in manual loop-based logic. This line demonstrates function composition. Here, the output of the student summary function is directly passed as the input to the sGrade function. By composing functions this way, we can build complex behavior from simple functions, making the code more concise, readable, and expressive. In this project, we clearly separate pure logic from impure input and output operations. All computations, such as calculating averages, are implemented as pure functions in processing.hs. Operations that involve reading files or printing output are isolated in IOHandler.hs. This separation makes the code easier to test, more reliable, and simpler to maintain, which is a key advantage of functional programming. Because our functions are pure, the program has the property called referential transparency. This means that an expression like student average S can always be replaced by its resulting value without changing the behavior of the program. This property makes the code easier to understand, debug, and reason about, which is one of the core benefits of functional programming.